There are 1,000 guides online showing you the different step-by-step methods to get a job. I need a job, and I realized getting a job is like solving a puzzle. So instead of applying for a job, I decided to build a puzzle solver. For fun, some people watch Netflix, scroll TikTok, play video games. I read GitHub. And let me tell you, there is just as much trash, petty drama, disappointing sequels. So one day I was in the bathroom just doom scrolling GitHub, as you do, and I discovered this puzzle solving repo boasting the best algorithmic complexity around, and it was well documented so I could actually understand it, and it had decent academic referencing, and it scratched that part of my mind that said, I can do it. And so I did. Much better. That sounds good, doesn't it? But it's not the real reason. You see, about a year ago, I was watching a video by Stuff Made Here, and I thought to myself, I can't do that. I can't do that either. There's definitely no fucking way I can do that. But this part that he's really struggling with, not only could I do it more accurately, not only could I do it more efficiently, faster, algorithmically speaking, but I could do it quite easily. And so my head filled with all these thoughts of how I could do it. CNNs, line detection, edge similarity, contour searching, and I decided I was going to do it. And then I forgot about it, and a year passed. Just after I finished filming, Mark Rober, aka Dr. Beast, aka NASA's X, aka the man with 1,000,000 balls, Orbi balls, he released his own video, and now I kind of have to clickbait him into the title and include his algorithm. The brute force method of solving a puzzle would be to test every different combination of puzzle pieces. This has an algorithmic complexity of n factorial. Stuff Made Here uses a search algorithm. He converts every edge into numbers and then uses a nearest neighbor algorithm to group similar edges. There may be multiple edges that fit, so what he does is then he finds a 4, like a 4-piece that all fit together. When there's 5,000 pieces, the chance of there being multiple 4s is low. If there are multiple, you can backtrack or search for just unique 4s, with minimal cost to the complexity. Since his aim was to solve just one problem, I'm sure he didn't implement backtracking. But the problem occurs when you increase the size of the puzzle. Say he averages 20 similar edges per piece when there are 5,000 pieces, then at 5 million pieces, it would jump to 20,000 similar edges per piece. The combination of different second and third pieces increases quadratically, and for any given combination, the number of estimated fourth pieces still remains linear. So even though it works well for a 5,000 piece puzzle, there are n squared options for each 4 square, and thus it's an inefficient algorithm. If backtracking is implemented, then the algorithmic complexity is going to be n factorial squared divided by the error rate to the power n, which simplifies to n factorial, the same as the brute force method. Maximus Roberto's algorithm groups edges by lengths before comparing, which is the same algorithmic complexity, but it saves some time. And instead of grouping 4s, he places 1 by 1 by 1 and then backtracks when an error is detected, which is pretty much the brute force method, but for a smaller selection of backtracks. Error scales with n, so if the chance that the correct fitting edge is the 10th best when there are 1,000 pieces, then there's the same chance it's in the 10,000th section when there are 1,000,000 pieces. Even if the possible edges are just 1% of the total edges, then the algorithm can be simplified to n factorial divided by the error rate to the power n, which simplifies to n factorial, the same as the brute force method. HJ2 Choi's version, on the other hand, instead of using white traditional pieces with like knobs and curly little bits, he's using colored squares, which sounds a lot easier, but it's really not. He can't use a search algorithm, so instead he has to use an optimization algorithm. So for every edge, he's essentially trying to find the best fitting edge in terms of color rather than in terms of contour. instead of breaking it up into 4 pieces and slowly building up the puzzle over time, he starts off with 1 piece. And then for this 1 piece, he's then tries to find the best fitting piece to this 1 piece. And then he finds the best fitting piece to this 2 block, the best fitting piece to this 3 block, and 4 block, 5 block, until the entire puzzle is done. The biggest problem with the HJ2 Choi's implementation is it can't deal with similar colors or any edge that isn't straight. The problem with the YouTuber's implementation is it can't deal with similar contours. The more similar they are, the more it has to backtrack and the slower the program is. If all the contours or all the edges are the same, it just can't solve the program at all. Mine can do both. Unlike the YouTubers, HJ2 Choi and I had an advantage. We were using software. We didn't have to worry about edges not being the perfect fit because we made them the perfect fit. We weren't competing on the same ground. So I sabotaged my puzzle creator. I gave it a mode where it purposefully was inaccurate with the contours. Essentially what I do is a combination of the two. A crossbred hybrid search optimization algorithm. First of all, I look at every edge and I calculate the contour for a subsection of that edge, and I place it into a hash map. We're going to call this the edge hash map, which if you don't know what a hash map is, I'm guessing you know what an edge is by now. I hope you do, otherwise this video is gobbledygook. A hash map is kind of like a dictionary. In Python it is literally called a dictionary. You have a key and a value. It's easy to look up the keys, and each key can have a subsection of values. It's hard to look up the values. So I set the key as the path, and I set the value as the puzzle piece and the edge number. So if there are multiple pieces with the same contour, then if I look up the contour, then I'll find all these different pieces and their edges that have this contour. So when I'm trying to find the best fit piece for a given square, all I need to do is calculate what the opposite edge should look like, what an edge that fits my edge should look like. And that's simple, that's easy to do, very quick. And then I find if there's 1 piece, perfect. If there's multiple pieces, then I just compare then I can compare the colors, or I can compare the contour parts. Easy peasy. And that's the main difference. If basically all the edges are the same, then it's more efficient for me to still create a similarity matrix. So that's what I do. I create a similarity matrix, and it's basically like HJ2 Joy's version, except for a few slight differences that improve my version. What he does when he's calculating a score, he compares one edge to a second edge. What I do is, when I'm trying to find the best next door piece, I take a look at the score, and then I took a look at the second best score. So that means if there's 2 white edges, then usually for his score, it would give it a 1. They're exactly the same, so they get a great score. But if I have like 5 white edges, I can have multiple 1 scores. And I don't know which ones work, so I shouldn't give it a score of 1. And so it looks at the best pairing of edges against the second best pairing of edges to give it a score, okay? That seems complicated, but it's very simple, trust me. Basically, I take the best value and the second best, and I minus them together to get the real score, okay? Easy, peasy, simple, slapdash, yes. Also, when placing a piece, I consider every neighbor, not just one neighbor. This sounds straightforward, but it's actually quite hard to implement, which is why H2 Joy probably just looked over it. Okay, that's the main differences. But now let's take a look. Let's take a crack at which is faster, which is more efficient. And instead of just running them, because that's boring, instead I will be looking at the algorithmic complexity. And oh look, why does it say that his is so much faster than mine? Huh, that's strange. Or is it? Well, it's because he's not considering P, and I'm considering P. And P is the length of the pixels of the side, because that's going to actually vastly affect how fast the performance is. And just like that, when you translate his into adjusting for P, oh, mine is faster. Yeah. But for mine, like the bottleneck, the thing that is slowest, is the loading the images and saving the images, which, like, if that's the bottleneck, if that's the thing that's slowest, and without that it would be a lot faster, and I'm pretty proud of my result. And it takes up a lot less space. I could change it so that instead of loading all the images at once, it just loads one image at a time, so then it takes up like a lot less space, especially if you have a massive puzzle. Unfortunately, it doesn't seem like I can input a job into my puzzle solver. If anyone can help me out with that in the comments, please let me know. If not, see you next week, potentially, maybe, who knows. Bye. If you want to know how I made these beautiful sunglasses, then my last video went in depth on how I topped the Twitch leaderboards and developed these incredibly hallucinogenic holographic sunglasses. And yes, I did it by hand. It was all me. CNNs, some shaders, and a lot of fucking trigonometry. More trigonometry than any one brain can handle. Beautiful, I know. Maybe not always beautiful. Okay, anyway, bye.